right. You're welcome to today's class. Today we want to look at ASCII table. What is ASCII? This is American Standard Code for Information Interchange. You know that if I have, what we've done so far is that I have tried to explain the concept of voltage at the physical level of the machine, right? Now, using transistors, we convert this voltage to what? To binary, which is 0 and 1. But even at that, the 0 and 1 doesn't make any sense. So how do we derive meaning from it? Using positional number systems, we can now obtain values in terms of decimal number from what? From binary digit. So that we have done. I've also demonstrated that for you to see. But how about representing text? Like, how are you able to understand what I'm saying? How is this going into the machine and then coming out for you to read and understand? It is because we had an agreed system. So to represent text, engineers had to come up with the concept of ASCII table, American Standard Code for Information Interchange. So what did we do? The first thing is I take a number. For example, I have 0, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 0, 1. I have this 1, 2, 3, 4, 5, 6, 7, 8. Now, when you look at this in itself, it doesn't make sense. There is no meaning. You're just saying 0 and 1. What does it mean? So the first thing we did, which I have taught you, was to use positional number system to give value to this, right? And then what we did was, in the case of binary, let's convert this to decimal. We are saying this represents 2 raised power what? 0. This is what? 2 raised power 1. This is 2 raised power 2. 2 raised power what? 3. 2 raised power what? 4. 2 raised power 5. 2 raised power 6. And then 2 raised power 7. Right? We are multiplying each of these. Doing that, this will give us 1. All this will be what? 0, 0, 0, 0, 0. Because you're multiplying whatever you get here with this. So that will give you 0. This is 2 raised power 6. So 2 raised power 6 is equals to what? 64. Multiplied by 1 will give you what? 64. Right? This is what? 0. So we are adding them up. So this will give us 65. So that is how this became what? 65. Using positional number system, we got this. All right. So how is not computer going to communicate with themselves using text, where you have A to Z? So that is where this concept of, or this table, this agreement came in. So it means that in itself, meaning is in the observer. Meaning is not inherent in the bit. So even the bit has no meaning. So what we agreed was to what? Assign this 65 to what? Capital A. It was not just random assignment. They did clear calculation to be able to achieve that, right? So what they did was they were asking themselves, if these are all the characters in English language, how many bits to represent? So they came up with about 120 something characters, maybe 122 or thereabout. So they looked at how many bits of binary will represent that number of characters. So if you say 2 raised power 7, that'd be what? 128. So if they had 122 characters, then this can cover it, right? So the initial ASCII was using what? 7 bits, which is 128, and that catered for what? 122 characters. So the first 0 to what? 31 characters were used for what? Control characters. Then you had numbers. So they represented 48 to what? 57 as what? 0 to 9. So 65 is A. Now, why did they pick 65 as A and then 97 as lowercase a? I will explain. So if we have 0, 1, 0, 0, 0, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. as what? 65. And this equals to what? Capital A. So we now have 97 equals to what? Lowercase a. Now, the difference between 97 and 65 is what? 32. So what this simply is telling you is that if I look at this, all I need to do is flip one bit in this, and I will get lowercase a. So if this is 0, and this is 1, this is 2, this is 3, this is 4, and this is 5, this is 6. If 6 will give me 64, it means 5 will give me what? 32. So all I need to do is flip this one. If I flip it to what? 1, this will give me what? This will give me 97. This. Because this is 32, this is 64, then plus 1, plus 1. This will give me what? 97. Right? So it wasn't a random guess. They did calculation. Very interesting engineering in order for them to come up with what? This ASCII table. But still, this ASCII table could not cater for all the characters in all the languages. That led to another one called Unicode. Contains all the characters of ASCII and then more. Because ASCII is using 8 bits, that will give you 256. Unicode is using 32 bits. So you can calculate how many characters that will cover. So far, they believe that in all languages in the world, their characters are well catered for in this Unicode. So this is how computer is able to speak all the languages for you to understand. So which means if we discover more languages, we'll probably have to come up with another agreed table. Understand? So this is encoding. So you are now encoding this. So at this layer, there's no meaning. So which means energy can neither be created nor destroyed, but can be converted from one form to another. Your breath, that is energy. Inside your blood is the algorithm that controls that energy to give you an output, which means your action. Whoever is observing that your action has a meaning interpreted, a meaning gives meaning to it based on what is already encoded inside the person. So in itself, this has no meaning unless we attach it to what? To the agreed table. So every time your CPU goes to the memory to pick values, what your CPU sees is 0 and 1. So there has to be a table that your CPU is going to compare these two. So that's why you're writing a programming language. When you're writing your program using any programming language, you must indicate the data type. Meaning you are telling the CPU, when you pick the value from this memory location, you must go to this RAM to get the interpretation to that 0 and 1. Without data type, the CPU will not know what the meaning of that 0 and 1 is. So that is what I want to show you. So this is the encoding method that is now embedded on top of what? The 0 and 1. So we have looked at different representation that brings about the meaning that we derive from what we are looking at in the computer. So that's what I want to show you in this class. So we'll move on. I'll show you how to perform some arithmetic on this 0 and 1 using half adder and a full adder, right? And then probably I will also show you a mathematical calculation of, say, maybe memory of 4 GB, right? So how many pattern would this represent? Then you will now see what AI is actually doing. That all what we are doing is what? Pattern recognition. As a human being, how fast can you recognize pattern in a realm? So how many pattern is the AI recognizing? Very fast. But you are also recognizing very fast. That is why you can give meaning to flower, give meaning to the things that you see. That is also pattern recognition, right? So that is what I want to show you in this class and how far we have come. So it is after we have done all this, then we'll look at data structure and algorithm, where this 0 and 1 is stored in the memory, and then how the algorithm goes to pick them and then manipulate them to give you the expected output. And once we are done with that, we can now come to the real realm of mathematics, where we are going to be looking at the different branches of mathematics and seeing how they are being used to create the technology that we are seeing in the world. That is my goal, based on my experience in more than a decade in the field. This is what I'm trying to give back to the community. So don't forget to give me a thumbs up, and don't forget to subscribe if you have not done so. So till we see in the next class. Bye-bye.